In the previous chapters, we have been talking about comparing our sample size to the population using a parameter. These are point estimates, so I can say how much of the population is going to be above this certain point. Point estimates are fine, but it's better to come up with an interval estimate to use to estimate your mean or any other parameter, maybe your variance or your proportion. These estimate intervals are called confidence intervals. So you can set an interval around the population mean that you're sure that your mean will fall into. Usually we do 2 standard deviations above and below the mean using a 95% confidence interval. Sometimes we use a 90% confidence interval, and you can even go as accurate as a 99% confidence interval. But again, a confidence interval is just an estimate of the range where we can expect our proportion or our population or our sample mean or sample variance to fall within. Okay, so I have some pictures so I can kind of show you. So let's say that we took a bunch of samples. I could tell you, comparing to my population mean, I can tell you that all of these samples, any sample you take, should fall within this range of numbers from my mean. Let's say I want a 95% confidence interval. So I'm telling you that your number should fall within about 2 of my mean. Okay. So your mean for your sample may or may not fall within the range that I give you, the interval that I give you, but it most likely will fall within that. I'm 95% sure that it will. Now let me show you another picture of just one sample. So let's say I took your sample, and by 95% confident, I'm looking at the middle 95%. So this leaves us with the 2 outside tails being 5%. Now notice that each one is split in half, and it's given notation alpha over 2. We use this notation in what's called a critical value. We can find this location using our table, and if you notice, it's really, really close to 2. Thinking back to the empirical rule, 95% of the data should be within 2 standard deviations. So our critical value is really, really close to 2. Again, this is denoted with Z with a subscript of alpha over 2. Usually they'll give us information like find a confidence, they'll either say find a 95% confidence interval or find a confidence interval with alpha equals 0.05. So you'll just have to pay attention to what the question is saying for that information. Okay, so we use 95% confident a lot. So it's good to memorize that when you're looking for a 95% confidence interval, the critical values are plus or minus 1.96. Remember, that's almost 2. Another confidence interval that we use a lot, maybe a 99% confidence interval, that gives us an alpha of 0.1, which gives us a 0.05 area in our 2 tails. That's going to be a 2.576. Oops. Said the right number, wrote the wrong one. There you go, 2.576. And sometimes we also use a 90% confidence interval with a critical value of 1.645. And again, that's symmetrical, so it's on the positive and the negative side because we're going to be running a 2-tailed test. Because we want the 95% area to be in the middle. Okay, so let me tell you how to find those numbers just in case you're curious. Now, if you're using the table, you have to be careful because we're doing, remember, area to the left. So we're going to find our alpha over 2. So again, 95% confidence is alpha is 0.05 divided by 2 is 0.025. So I'm going to make sure you know how to do this on the table to find this number. And notice that I'm using the smaller one because they're symmetrical. If I use the larger one, the shaded 95% will be down here instead of in the middle. So that's very important that you use the smaller tail to find your z's, just in case we don't have 95, 99, or 90. Okay, so I'm looking for an area. So this time I'm going to look in the larger portion of the table instead of the edges, and the number that I'm looking for is going to be on the outside. So I'm looking for 0.025. Okay, 0.025 is right here. So my critical value is 1.96 negative. And because I know it's symmetrical, we're going to use also a positive. So that's how you get this number. If you were looking for a 90% confidence interval, then the tail, if this area was 90%, oops, you can't see me, then this tail would be split the other 10%, leaving this 5%. So if I'm looking for 5%, I'd come in this area again, and I'm looking for 0.05, but I only have 0.0505 and 0.495. So it's going to be negative 1.64, and then halfway between would be 5. So the critical value for 90 is 1.645, both positive and negative. Okay, so I hope you understand how I got those numbers. We're going to use the critical values in our formulas because we're going to need to multiply it by what kind of looks like our standard deviation and then add it to our parameter. But we need to first, again, remember that this works because of the central limit theorem. So I need to make sure my sample size is larger than 30, and my standard deviation and my mean are approximately normal. And this looks like it's your standard deviation because it is your formula for your margin of error. So if Alex asks for margin of error, E, that is this ending of this formula right here. On the side 2, that's your margin of error. Okay, so let's just try some problems out. The concept is we're getting an interval of this number and this number, and any mean that we find should fall within that number. Mean, proportion, variance, whatever. So we're going to do some means, we're going to do some proportions, and we're going to do some variances, and we're going to figure out what this means. One of the population of millions, of the population of millions of American children who had their teeth checked at a dentist in the past year, a random sample of 75 was taken. And it is found that 42 of these children had decaying teeth. Use the data to find a 95% confidence interval of P, the mean number of children who have decaying teeth in America. Okay. So we're going to use this study to make an estimate of the population. So I need an interval of where we can estimate that the actual number of children have. Or any study that I run, we should find that our data, our mean, falls within this interval that I'm going to find. So let's look at our statistic. Is it our statistic? Yes, because we're looking at our sample. So our statistic is that P hat is equal to 42 over 75. So we can find, I don't know what's happening, just a second. There we go. we can find the proportion of the children in our study that had decaying teeth. So there's 56% of the study's children have decaying teeth. If I want a 95% confidence interval, that means I want to be 95% sure that your mean is going to fall here within mine. Okay, well, that's a beautiful picture. Hang on. So this is going to be 95%. That means this tail is half of 50%, which is 0.025, and this one is 0.025. Okay. Let's figure out what, I guess I could call it E is. We have the square root of, I'm using this formula right here, p hat, which is 0.56, times 1 minus p hat, which is q, which is 0.44, divided by our sample of 75, and that'll give us 0.057. Okay, so according to the formula, I can take my proportion and add and subtract 2 standard deviations, right? Or do 1.96, almost 2, times, I guess I should, hang on, let me write it for you. We have z alpha over 2 times our standard deviation of p hat. Okay, so that is 0.56 plus or minus 1.96 times 0.057. So this is 2 numbers here, one where you add and one where you subtract. So that gives you 2 answers. My smallest answer being 0.448 and my largest being 0.672. Those are the numbers here, 0.448 on my my sample that correspond with those critical values of 1.96 and negative 1.96 on the standard normal curve. Okay, so what the heck did we just find? We just found that we are 95% confident that the true mean numbers of children, oops, ran out of space, who have decaying teeth in America is between 44.6 and 67.2%. In America, you cannot read that. So any sample that I take, I should find that I have a mean, 95% of the time, I should find that I have a mean that falls between 44 and 67% of the sample have decaying teeth. So it's very helpful for us when we're estimating things about the population or we're estimating things about our sample. Okay, let's try another one. 54 of 180 randomly selected credit card purchase slips from the thousands written were made with a Visa credit card at a department store. Use the data to find a 90% confidence interval for P, the mean number of Visa transactions made in the department store. Okay, so we're looking at our statistic here. P hat is going to be 54 out of 180, which gives us 0.3. Okay, so from there we know that our standard error is 0.3 times 0.7 divided by the 180 in our sample, which gives us approximately, let me see. Okay, I calculated that to be 0.034157. I just left all those decimals so we can be as accurate as possible. Okay, so now I need to check my confidence interval. So we want a 90% confidence interval. So we want, I'll draw you a picture. Okay, that means our alpha is 10%, so we need to split that 10% into the two tails to give us 0.05. We have 90% of the data in here around our 0.03. Now I know from the beginning or from my table that that critical value is negative and positive 1.64. So now if I go ahead and use my formula and plug in all these values, I can find a confidence interval for those numbers compared to my actual sample. Wow, I'm losing words today. Okay, so we have P hat plus or minus Z alpha over 2 times sigma of P hat. That gives me 0.3 plus or minus 1.64 times 0.034157, or the square root of 0.3 times 0.7 over 180. However you want to put it in your calculator. You don't have to calculate them separately. This gives us an interval of 0.244 to 0.356. And you just plug that into your calculator and it'll give you some numbers. Or I don't recommend doing that by hand. Okay, so we can say that we are 90% confident that the true mean number, and basically right here I am copying the question again. We are 90% confident that the mean number of Visa transactions, so I'm just rewriting that, is between, and then I'm going to input my answers. So I just restate the question and then input my confidence interval between 24.4% and 35.6%. Okay. Why does that even matter, right? It would only matter if maybe I was in the store and my Visa machine went down or I lost the internet, right? I would know just how much percentage of my transactions I've lost because that happened. So that's a good piece of information to have, depending on what you're looking for in your business. Okay, now we have some examples. Instead of with proportions, we have some mean examples. So a study is being conducted on middle-aged men on a diet by Dr. Adams. For a random sample of 64 middle-aged men on a diet, Dr. Adams found they have a mean fat intake of 37 grams and a standard deviation of fat intake of 32 grams. Find the statistics that represent the sample and a 95% confidence interval for the actual mean fat intake mu. Okay, so I'm just going to write down what we know. We know that N is 64. We know the standard deviation of the sample is 32, and the standard mean of the sample is 37. I can use the formula X bar plus or minus. Oh, actually, let's get to that in just a second. Wants us to find the statistics that represent the sample in a 95% confidence interval. Okay. Because we have a known standard deviation, this is straightforward following the formula. So that is X bar plus or minus the critical value, alpha over 2, times the standard deviation divided by the square root of the sample size. Okay, we have a 95% confidence interval, so we know that our critical value is, we know everything, so we just need to input that information. 37 plus or minus 1.96 times 32 divided by the square root of 64. Now I was looking at the calculator, how the book sets this information up in the examples. They write it so that one is on the left and one is on the right, and it has like the minus and the plus in different spots. And that's so that you can visually see what's going on. But you're just doing two pieces of information. 37 plus 1.96 times the standard error, and then a version of it when you use subtraction. Okay, I calculated 29.16 to 44.84. So between 29% and 45%. So we are 95% confident that the true mean fat intake of middle-aged men on a diet is between, it's not percent, 29.16 and 44.84 grams. Okay, Robert is conducting a survey for the average teacher salary in Texas. He has 40 participants from schools all through Texas and has determined the teachers should have mean annual salary of about $56,000 with a standard deviation in salary of 15. Determine an 80% confidence interval for the mean salary of teachers in Texas. Okay, so we have a sample of 40. Small sample, still large enough to be considered large. Compared to the number of teachers, but that's okay. The mean of the sample is 56,000, and the standard deviation of the sample is 15. Because we have this information, we can use this method. We have a bigger than 30 sample, we have the standard deviation for the sample. So I can take X bar and add the critical value multiplied times standard deviation divided by the square root of the sample size. Okay. Goodness gracious. Okay, 56 plus or minus, what confidence level? 80% confidence. I need to go find that number. So that means, my bell curve is getting funky looking. I want 80% here. Means my tail is 10%. Okay, so on my chart, this is as close as I'm getting to 10%. So negative 1.28. Now I believe that we normally use negative 1.282 just because it's not accurate on the table. And I got that from using the calculator function where I found the inverse normal. I can post some videos with calculator for inverse normal and for confidence interval. If you want me to do anything that I haven't done, just to reach out to me, and I'll get that made for you. Right now I'm just filling in my formula. Okay, so I'm going to plug these numbers in and I'm going to get, okay, so I've got $52,960.50 for my lower and $59,000 for my upper number. I'm just realizing as I finish these problems that these two problems should have said that the population standard deviation of intake fat was 32 grams, and the population salary, not the sample population, the population, the standard deviation of the population, not the sample. That's how you know that you can use a normal distribution, because we have an approximate population standard deviation. Okay. Now, sometimes you don't, and that's when you have to use a different distribution altogether. So if you have a small sample size, or you're not given the standard deviation of the population, then you have to use what's called a t-distribution. So sometimes in the problem, it'll say that we can expect it to follow a normal distribution, or that it is assumed that the population is normally distributed. That's very helpful for us. We'll then use a t-distribution for these problems if we don't have a standard deviation. Okay, a t-distribution is all different sizes. We've used them in chapter 10 a little bit, so that was a little bit out of order. This distribution, it's a family of distributions, just like the normal distribution, but it's approximately normal. It has more tell area than the standard normal, so it's not following the empirical rule. We use what's called the degrees of freedom to figure out which distribution we're using, so that's n-1. Our critical value, instead of a z value, is a t alpha over 2, so it's still a two-tailed test. We're just using a t for t distribution instead of z for normal. The confidence interval is plus or minus the error bound. So that is the same formula that we're using in the last two problems. Okay. So this time we're given data, which is going to make this harder. I don't know how well this is going to turn out, but I'm going to try it. My calculator is dead, so I can make a new video to show you how to do this. This is Excel. I've gone ahead and put this problem in Excel. In example 1, Ashley opened a bag containing 60 chocolate chip cookies. She selected at random 20 cookies and counted their chips. So we have a table of the cookies, and then she made a note of how many chips in each cookie. So that we can find the average number of chips in each cookie. The question asks us to find the mean and the standard deviation. So you can do this in your calculator, but it's easy in Excel also. Remember that you do need your data analysis package added. So I'm going to go to data analysis. I'm going to select descriptive statistics. This is probably really terrible. The view is bad, but anyway, so descriptive statistics. It asks us what columns. Yours will pop up blank. I just ran it to make sure. So I'm going to select the chip column. I don't care what cookie had what chip, but I do want to make sure that I've labeled the first row. I'm selecting an output range. I want summary statistics. We're not going to do the confidence interval right now, but I want a summary of the statistics. This is going to give me my mean, my standard deviation, and also shows us that my median and my mode are the same. So we already know that this is approximately normal. So even though the problem forgot to state that this is approximately normal, because the mean, median, and mode are all lined up, I can tell that information. Now what do I need for here is I need the mean, which is 8 and the standard deviation, which is 1.589. If you caught that a second ago, I can also find my I can find my confidence interval this way too. You're just going to select the confidence interval down here. In this problem, they want a 90% confidence interval, so I'm going to make sure this is at 90. But I need you to be careful here. This is only going to give us, and it's here down at the bottom, the number that we're going to add or subtract from the mean. So we're going to add 0.615 and subtract that from the mean of 8, and that'll give us our confidence interval. Okay, so let me write down everything that I found. So I wanted to show you that you don't have to do this information by hand. Excel will do it for you because the formula for this will take you a while. You have to find the mean and the standard deviation here. So the mean of the sample is, what did we find out? That it's 8, and the sample standard deviation is 1.589. Okay, if it's asking us to estimate the mean within a confidence interval, that's what we just found. We're going to do x bar plus or minus t alpha over 2, goodness gracious, times the standard deviation divided by the square root of n. So we don't know the population standard deviation of the total chips. We didn't look at the company, we didn't contact them, we don't know what we can expect to be in each chocolate chip cookie. So we have to use the t-distribution for this case. There is another table for the t-distribution if you don't like using Excel. Let me get it for you. Okay, so I went ahead for a second and wrote out a couple more terms of the standard deviation from my Excel spreadsheet because I'm going to need a better estimate of this information. Okay, so this is the t-distribution table. We're looking for your confidence interval of 90%. So we're going to be looking in this column. And then the degrees of freedom is your sample size minus 1. N minus 1. So we're looking for degrees of freedom of 19. And I found it and marked it already. 90% confident, 1.729. That is our critical value. So what we're going to do here is 8 plus or minus 729 times our 1.589438 divided by the square root of 20. And again, I chose this number because I know that it didn't come out right when I ran it with the short decimal. So to make it more accurate, I extended it. This gives me the same number in the calculator, 6.6145 that we saw in Excel, that we're going to add to and subtract from 8. So 8 minus this number is 7. I didn't leave myself any space. Sorry, 7.386 to 8.6145. Yeah, I should have known that. 8.6145. So 615. Okay, so I'm 90% confident that the mean number, the average number of chips in a cookie is between 7.38 and 8.62. Using this confident interval, what assumptions are we making about the sample and or the population? Okay, so in order to do this, in order to use the t-distribution with a sample that had no population standard deviation, I had to assume that it was approximately normal. So we assume the population is normally distributed. Now this should have came in the problem, but we did see it in our data about the sample. Okay, estimate the total number of chips and the remaining 40 cookies. So if I wanted an average number of chips and the rest of the container and the 40 leftover cookies, I could multiply my confidence interval by 40 to get an average approximation of how many chocolate chips are left in the bag. So I'm going to multiply the lower bound by 40. I'm going to multiply the upper bound by 40. I don't know why I wrote it differently each time, but I did. Okay, so that gives me approximately 295 to 345 chips in the bag. Okay, let's do some more. I have another example. I have another example. I do, but it's another example that I have data. So I'm going to put this in the spreadsheet and then I'll come back with some information. We also need to assume that this follows a normal distribution. Now again, that should be in the problem. I just made a mistake. So I have well, if you know, in my in-person classes, they actually do studies, and this student got to collect data on screen time of students who were taking statistics. So here are some data below. I typed that into my Excel and found that the mean of this sample is 4.6075, and the standard deviation of the sample is approximately 2.0907. Okay, we want 98% confidence, so I need to find my critical value. I have 20 people, so that's a degrees of freedom of 19, and I want 98% confidence. So 98% confidence with a degrees of freedom of 18 gives me a number of 2.552 for my critical value. 2.552. Okay, I'm going to multiply that times my standard deviation divided by the square root of 20 and add and subtract that from 4.6075 to get my confidence interval. 2.0907 divided by the square root of 20. And that gives me a confidence interval of, I realized that I used 18 degrees of freedom instead of 19, so I went back to my table and found my 2.539. I'm sorry if you caught that before I did. Okay, so that gives me an interval of 3.42 to 5.79. Okay, so I know that I'm 98% confident that the mean number of hours a statistics student will spend on their phone is between 3 and 5.7, 3.4 and 5.7 hours. Okay, I'm almost done with this chapter. I need to do a sample size. How do we choose a sample size? There are some formulas for this. So we need to do a couple examples. We can use the error bound and the confidence level that we want to find the required sample size. So we can say we want to be this confident. We expect this much of an error. Thus, we need this large or this small of a sample. The best way to do it is just to do some problems here. So we have example 1. Oh, there's a couple things you need to know. I'm sorry. If you have no prior knowledge about the proportion to succeed, then you assume that the probability of success is 0.05 and that Q is 0.05. We assume that it's 50-50. So if you have no prior knowledge, that's the equivalent of not knowing what the population standard deviation is. And on this one, you take the range of your numbers and you divide it by 4 to get your quartiles. Okay, suppose you'd like to estimate the proportion of people who watched a new television show. With no prior knowledge of this proportion, how large a sample would you need if you want to be 95% confident that your estimate is within 3% of the true value? Okay, so we have some things. We have no information, right? So we're going to assume that 50-50 here. You watch it or you don't, right? We have an error of 0.03 in my z. My critical value, alpha over 2, since it's 95%, is 1.96. These problems should also assume normality, and I just left it off the examples. Okay, so it just takes you plugging that information in. We're going to square that 1.96 to give us our spread. We're going to multiply times the probability of success and failure, and then divide by the error that we want. And then that gives us a number of people we should sample. And you always want to round up when you're finding this information. So we should do a sample of over 1,000 people to have only a 3% error. In order to comply with No Child Left Behind Act, states must create ways of assessing students' achievement, and it is essential for a state to be able to accurately predict how a student will do on the test they devise. Suppose your state's Department of Education would like to estimate the mean score of a 100-point math test being designed for Algebra 1. How large a sample will you need to estimate the mean within 2 points of with 95% confidence? Assume that the data from similar tests used indicates that S equals 15. Okay, so we have some information. We know the sample. That should definitely be sigma, not S. Smaller test, hang on, assuming the data from smaller tests used indicates. Yeah, that should be a population. Anyways. Okay, so first reading this question, it doesn't make any sense. The most information you need is in this last sentence. So if you're stuck on a problem, just try reading the last sentence again and see if it follows any of these problems that I've tried. Okay, how large a sample? So that's what we're looking for. We're not estimating a confidence interval. We want to be 95% confident that our mean falls within the 2 standard deviations of our population, but we want to know how large a sample we need to take in our own sample to get an accurate number here. So we're going to say that the numbers that we need to sample is going to be our 95% is 1.96 again. And then we're going to square that and multiply times the standard deviation of the population squared and divided by the error squared. Okay. That gives us 216 and 1/9 of a person. So we'll say that we'll sample 217 people, and we should fall we should fall within, our mean should fall within that confidence interval. I can't spell people today. I'm struggling. Okay. Well, I think that's it for confidence interval. I can do a couple problems on the screen if you need me to for the calculator, because this, you can type this right in the calculator. Actually, I can tell you the calculator strokes right now if you'd like, instead of making a whole video. If you do open a calculator and do menu, statistics, confidence interval. If you're doing a proportion, make sure you do a 1 prop z interval. If you're doing a mean or a variance, you're doing a normal z interval or a t interval based on what information you have in the problem. I can swing that over. It just looks really bad from this view. Okay, so again, if you need to see that, that is, let me get out of here, statistics. So menu, statistics, confidence intervals, and then again, proportion is 1 prop z. We're not doing 2 proportion yet. You should have also a z interval if you know the sample, the population standard deviation, and then a t interval for not knowing the population information. When you're hitting z interval, you don't want to enter data unless you have a data problem. You want to hit stats, and then you'll put the information from the problem and change your confidence interval, and then it'll spit out your information. I'll have an example here. So your C lower and C upper are your confidence interval. It'll find your mean, your margin of error, and your sample size and everything in there as well. Okay, if you want me to make a video using that information, just send me a quick email or put it in the discussion board.